I'm originally from Africa, Central Africa, from parents originally from Rwanda, but raised in Congo, back then was Zaire, and then went to high school, a Jesuit school. Very in love with soccer back then, and then played with others. My dream back then was really to become a soccer player. My parents kept on pushing us to stay in school, and then with the Jesuit around, we had a very strong community, kind of encourage education, which is what is the strength for the Jesuit. And I'm happy that I was able to stay in that boarding school, and I finished high school. And after high school, I took a national exam that I was able to pass and win a scholarship to come to the United States after finishing my, my college, my bachelor degree in Congo. And that's how I ended up coming to the United States. How did I end up into high-performance computing? I'm an engineer, civil engineering by training. I got my PhD in civil engineering. But when I was selecting my PhD thesis, the topic was really related to computational. And I was very excited because coming from a university where we had access to only one computer for the whole school, you can imagine that we didn't have access to that computer. It was actually reserved to the faculty. But we had a computer programming class without a computer. And we'll write Fortran code, as a matter of fact, and we'll compile them during the test and debug them, and without even having access to the computer. And you just imagine the error messages that you will potentially encounter, and then how you will solve that. And then having access to a machine at the university in the US was something that I was fascinated about. And then that was actually also the beginning, because we did everything on paper. And then to be able to write a program that can do it quickly was something that I was really fascinated. And then after that, I had access to the first Cray, trying to write and accelerate code, and that was the beginning of it. Currently, my inspiration for the moment is really high-performance computing. It's scaling applications to large core counts. You hear today petascale, and now they are talking about exascale. The hardware is there, but I do not believe the software and the applications are there. And then we also now start rethinking every piece of algorithm. How can we rewrite this algorithm to take advantage of this hardware that are becoming available to us? As we think about those, how to do that, with the purpose of doing an impact, of pushing science, and how that we can solve more and more challenging problems. Nowadays, it's becoming customary. You go to the doctor, you get the CT scans. It's becoming routine, basically, could do a reconstruction, for example, of your body. Imagine once if a doctor could be able, virtually, go into your anatomy, open your heart, and identify your disease, identify an aneurysm, and be able to think about the procedure it's going to perform to you tomorrow. That will make a big difference, because he'll be well prepared. He will know what he's going to do. Not only you minimize the invasion of invading your body without knowing what they're going to proceed as a procedure, but it's also helping to be more accurate. And I can give you many examples as we move into personalized medicine, as we try to resolve issues in climate, and then in astrophysics, and all sciences. And that's, for me, the inspiration that will keep me excited every single day. So what I see as big challenges to make progress at this junction, there are two things happening. As a matter, we should also redefine how we think in terms of high-performance computing. Traditionally, we used to think of it as cycles. With the explosion of data, there's more data coming out of experiments. There is more data being generated from simulations of these large-scale runs. How do you visualize the data? How do you manage from the data from an experiment, for example, from a proteomics lab or genomics lab that has next generation sequencers that is generating a lot of terabytes of data, moving from that core facility to your supercomputing center where the person then will be able to analyze the data movement. All of that because you can think in terms of workflow, trying to build also how do you leverage the back-end high-performance computing cluster that will then analyze a huge amount of data, or how you can refine your simulations to scale to thousands. We can write code today that scales to 64-256, but when you start talking about a code that would run on the top #1 system, it's all a different ball game. It's a rewrite, a rethink on how you can communicate among all those thousands and thousands of cores that are connected together. Those are really challenging problems that we see today. There are quite a lot of work going on. The Minnesota Supercomputing Institute support a large number of principal investigators. We currently have more than 500 principal investigators at the university. And then when you count their collaborators, we have more than 4,000 users. One of the things they are really pushing more is what I always refer to as interactive supercomputing. The ability to be able to, say run a calculation on 8,000 cores, for example, and then collect the data and be able to visualize the result while the computation is running, and then hopefully, if possible, to steer even the calculation. That's kind of what the trend is, because a lot of the simulation data being generated are pretty substantial. To be able to process that in a very short period of time, it's a challenge. The ability today of being able to do reconstruction, image reconstruction from CT scan, MRI scan, and be able to generate meshes that can be used with finite element packages like ANSYS or Abacus and so forth. I've opened up an ability to do a lot of the virtual reality analysis and design. You can take the example of medical devices, for example, where you can take a real-life reconstruction of a heart of a patient or a live patient, and then be able to add, let's say, the flow or the fluid, for example. Can you imagine if we can be able to put a medical device, see how it sits or how it reacts to the flow of blood, and be able to do that without invading the patient? Or the medical device engineer who is trying to model a brand new device to understand the structure, fluid structure interaction, and if you can do that in an integrated environment. That's something I see we are moving. As we start talking about personalized medicine, a lot of that will become, we should be able to move that stage to start kind of making this automatic. My vision is the integration of high-performance computing, because it's something we cannot ignore anymore. We have to go that route. It's a route we have to take, and then it's a route that we have to successfully integrate. But we need to look beyond that. Once we have already be able to successfully make use of a high-performance computer, what will be our next target after that? What will be heading after that? What will be able to do after a computer is part of a chip that I will have under my skin, that will have all my bio data, for example. And then you start now thinking in terms of what are the ethical implications, and those are the questions that we are actually not discussing today. Those will become also very important as we look in the future. What inspires me is when I look at my 3 children, 8 years old, 6 years old, and 2 years old, and I look where I came from this remote area in Africa and where I became here in the US. I always view that in that mirror, seeing my children becoming somebody and then embracing the same route and motivated to do also science. Every single day when I look at that picture, it's really a source of my inspiration.